So for the next talk, it's my pleasure to welcome Sushmita Venugopalan, my colleague from IMSC, and she's going to tell us about counting curves tropically.
Thank you for the invitation. Let me start by asking the only question in this talk which you can answer. If I give you two distinct points in R2, the plane, how many lines are there through the two points? So it's one line, right? So, and this analog, you can ask analogous questions in complex space, C2, and now we are talking about complex lines. And again, the geometry is the same, and you just get one complex line passing through 2 points in C2. And let's make it slightly more complicated. So instead of C2, let me talk about complex projective space in 2 dimensions, which you may think of as like a compactification of C2, in which the lines at infinity are at you add lines at infinities, and they are kind of at par with other lines in C2. So the same thing what we observe in C2 continues to be true in complex projective space also, which is CP2, but I'll drop the field and just talk about, refer to it as P2. The answer to the first 3 questions is just one line through 2 given points. So the title of my talk is Counting Curves Tropically. So my first job is to just tell you what I mean by counting curves. So that's where I'm getting to here. So typically when I'm talking about counting curves, I'm talking about counting parametrized curves. So in the case of projective space, lines should actually be thought of as spheres, like compactified lines. So complex line is a C, and when you compactify it, it's an S2. So when you parametrize such lines, these are actually linear maps from P1 to P2, which have that form in homogeneous coordinates. Okay, so we are talking about parametrized lines. So then we also have to account for the fact that reparametrizing the domain should not give you a different line. So we need to take the space of all linear maps and mod out by domain automorphisms, and then look at these objects and then constrain them to pass through 2 fixed points. So in some sense, this problem is same as the preceding 3 problems which felt more intuitive. It's only that I'm parametrizing the domain and modding out by domain reparametrizations. Okay, so that's counting curves in degree 1. And we can ask the same question in for higher degree. So if I look at degree D maps, what I'm really asking for is those linear maps there get replaced by degree D homogeneous polynomials. So those P0, P1, and P2 are homogeneous polynomials of degree D. And again, I mod out by reparametrizations of the domain and require that the image contains instead of 2 fixed points. So now when I'm talking about degree D polynomials, it has a whole lot of coefficients, so there is the degree of freedom is much higher. So to make sure that we get isolated solutions, if there is a solution, you shouldn't be able to kind of move it and get a whole continuous family. In order to ensure that the set of solutions is unique, you need to fix 3D minus 1 points and constrain your map to contain those 3D minus 1 points in its image. And if you do that, the answer is a discrete number, and we denote this number by ND. And in the first, N1 and N2 are 1 is elementary. N1 is 1 is what we saw in the last slide. And N2 is 1 is the result which is kind of a classic elementary result, which says that there is exactly 1 quadric passing through 5 generic points. So if you start doing some algebraic geometry, that's like one of the first things you see, and it's something you can actually calculate by hand if you, just work with those. You take quadratic polynomials and constrain them to pass through 5 generic points. But 3 onwards, it gets complicated. 3 was computed in 1848. 4 took more time, 1873, and after that people were stuck until 1994 when Kontsevich gave a recursive formula for ND, kind of revolutionizing the field. Okay, so this field, so this problem of counting curves in P2 can be extended to counting curves in other manifolds or other projective varieties, and the study of these problems is done under the name of Gromov-Witten theory, and these are called Gromov-Witten invariants. And one of the biggest problems you encounter when you start counting curves in spaces which are more complicated than P2 is that that curves that should not exist for index reasons actually exist. Like even in the P2 case, if you take points which are not generic, so suppose you take all your points lying on one line, then you get like a whole lot of curves which should not exist generically, but so in some sense, so you can kind of assign like an index to every curve, and if the index is negative, that curve should not exist, but they nevertheless exist. So for that reason, so that's what makes the question somewhat complicated. And in symplectic geometry, which is the field I work in, the way we deal with this problem is to perturb the complex structure. So, so essentially, these maps that we are talking about, these maps U, which I mentioned in the previous slides, these are solutions of a partial differential equation, which says that these maps should be complex linear. So that complex linearity is a partial differential equation, and perturbing the almost complex structure involves introducing a perturbation so that only the ones which you expect to exist actually exist. So that's how symplectic geometers think about curve counting problems. Anyway, so much for abstraction. Let me actually get down to some pictures now. So I'm, from here, I kind of, this is like a next section of the talk where I talk of, if you're zoned out with all this technical nonsense, can come back. So I'm going to talk about something called tropical curves, which don't look like curves at all. These are not maps or functions or anything. They are literally combinatorial object called graphs. So what are tropical curves? So we are talking about tropical curves lying in R2. So these are graphs which lie in R2 and whose edge slopes. So each of these edge has a rational slope, so a rational element of R2 associated to it, and those numbers add up to 0 at any of the nodes. So I'm hoping that is obvious from the picture, because in most of the nodes my slopes are just -1, 0, 0, -1 and 1, 1. So those add up to 0 at the junctions, and there's just one example where there's a slightly different slope involved. So that's what these tropical curves are, and another condition is that their infinite edges have these fixed slopes. So, that's again something you can verify in all 3 pictures, that there are three kinds of slopes that occur for the infinite edges. So infinite edges are edges which just have one vertex and are just going out to infinity on the other side. Questions? So it's not slope in the conventional sense. It's you take the slope and associate a z square, a tuple of 2 integers to it, which is in the primitive form, making sure there are no common factors. So that's the slope. So I have labeled these some of the edges by their slopes. I have time for one more question. Okay. So if, and also notice that the number of infinite edges in each of these three directions determines the degree of the tropical curve. So the degree, again, that is something that is obvious from these three pictures of a degree 1, degree 2, and degree 3 tropical curve. Okay, now the remarkable thing is that if we do the same thing with tropical curves, if you fix 3D minus 1 generic points in R2 and you look at degree D tropical curves passing through those fixed points, then that set is going to be a discrete set. It's not a continuous family. Similar to what we saw in curves earlier. And this number, the number of degree D tropical curves through 3D minus 1 points is equal to ND, which was the number of rational curves of degree D in P2, which we defined earlier. And this is a result proved by Meghalkin in 2004, which kind of started the study of tropical geometry. It suddenly became an interesting field. And the name tropical itself comes from something done by a computer scientist. Like they defined a tropical semi-ring where the addition and the multiplication operations are replaced by multiplication and minimum operation. And so if you take that algebra and look at the hypersurfaces of polynomials, you will get these surfaces. And that the computer scientist who invented that happened to be living in Brazil, so it got the name tropical. Okay, so that is about tropical curves. Now, let me move on to the stuff I have been working on and connect this to Meghalkin's result. So that's what I'll be doing in the second half of my talk. So, so I'll start by defining a notion of how to cut a symplectic manifold. So if you have not, yeah, so I won't really deal with the definition of a symplectic manifold, just think of it as a space, you know, which looks locally like Euclidean space, and it has a certain kind of 2 form on it, again, which is not important for this talk. So anyway, so if you have a symplectic manifold, in order to cut it, you need some inputs, and the first input is a separating hypersurface. So Z is a codimension 1 hypersurface sitting inside X, and in the neighborhood of X, neighborhood of this hypersurface, you have an S1 action, which is, again, reasonably behaved with respect to the symplectic structure. And if you have such a thing, you can perform a symplectic cut. And what a symplectic cut does is it separates the manifold along this hypersurface, but then it becomes a manifold with boundary, right? So to kind of get rid of the boundary, what you do is you mod out the boundary by the S1 action, so that in the end, the result you get are actually closed manifolds. They don't have boundaries, and the Z mod S1, which sits inside both of them, is a codimension 2 submanifold, or a divisor, or a subspace, however you like to, whatever word is most comfortable for you. So, I mean, it kind of, closes up. So if you, the easiest example you can think of is if you have a cylinder or a sphere, something like that, so this is a sphere, and if I cut it along the middle and mod out this boundary by the S1 action, then I get 2 spheres, right? So I get rid of the boundary by modding out by S1. So that's what a symplectic cut does, and in general, this operation always produces smooth manifolds. And both of them contain a copy of the Z mod S1. Okay, now my question is, yeah, so I'm going to ask a question which is unrelated to everything I have said so far, and this is actually the work, the stuff I have been working on, is that if we, can we relate counts of curves in the manifold X to the counts of curves in the pieces? And to start thinking of the thinking about the problem, what we do is we take the manifold X and kind of stretch the neck region, like the Z along which we were cutting the manifold, we stretch that region. And by stretching, I mean I'm changing the almost complex structure on it. So that's a slightly technical term, but for the layman, you should just think of it as just think of this picture as if you're stretching the neck region so that eventually they two come apart, the two things. But in the mathematical quantity that is changing is the almost complex structure. And then we look at curves in these neck stretched manifolds and then look at their limit as the neck length goes to infinity. Okay, and then what we see is this is what typically happens to curves. They get stretched, and some part of the curve goes into x plus, some of the part goes into x minus, and some of the stuff remains stuck in the neck, as you can see in the picture. And these kinds of maps, they are called broken maps. And they typically have a components in x plus, x minus, and in the middle, which is the neck. So the target space of a broken map is a broken manifold, which is the pieces obtained by the symplectic cut and the neck piece. And this result is kind of a famous result by now. It's been a field of research for the last, I don't know, since 2000, so the last 20 years, is that you can show that there is a bijection so the curve counts for in the neck stretched manifold is same as the curve count in the broken manifold. So you can kind of go back and forth between them. Yeah, and this is kind of more of the same. So this is sequence of, if you take a sequence of maps in neck stretched manifolds, as the neck length goes to infinity, it converges to maps, broken maps, which look like those maps on the right side. Okay, so what we were looking at is what if we do this, apply multiple cuts simultaneously. And that's been, technically hard enough that there is some literature available, but mostly nobody understood it. And so, we kind of worked out everything and wrote it up, which took a long time and filled in many details which were not very well known. So that's what I was working on. And so we proceed in a similar way. If there is a cut, the region surrounding it is the neck region, and you stretch it to produce many pieces. So the neck pieces are of various different forms. So those 4 corner pieces are obtained from the cut, and the ones with the blue stripes are all various kinds of neck pieces. And that's the broken manifold. And this is kind of a more abstract picture of it. The top one is a multiple cut. You stretch the neck, and you get a broken manifold, where the blue ones are the neck pieces. And when you look at limits of curves for these sequences of neck stretched manifolds, that's the picture you get. So you get the expected limit, but in addition, you get an additional piece of combinatorial data, which is the tropical graph, which looks a lot like the tropical curves we saw earlier. So we have a vertex corresponding to each of the curve components, and they are connected by lines with rational slope. So a broken map comes with an additional data of tropical graph. And one of the main technical results of our paper is that you can go back and forth in the multiple cut situation also, that there is a bijection between curves in neck stretched manifolds and curves in the broken manifold. And finally, to finish my talk, I'm on time, right? Okay, yes, so I want to relate what we saw earlier with Mihalkin's tropical curves and our broken maps. So Mihalkin's tropical curves are actually a specific occurrence of broken maps. So they are, so if you take P2 and cut it in that manner, so neck stretched manifolds have this shape, and it turns out that if given a Mihalkin's tropical curve, it corresponds to a unique broken map, in the sense that you literally take the Mihalkin graph and that is the tropical graph of our broken map. So, like in what happens is that you literally copy the Mihalkin graph, you take the tropical graph, and this the maps for all those vertices are uniquely determined. So, so this is just Mihalkin. What did it was an example of the story of broken maps and neck stretching, and I'll stop here.
Thanks a lot, Sushmita.